Okay, so in this video, I'm going to be marking a guy's um, worksheet. Okay, yeah, his name is not censored in any way whatsoever, so alright, I hope he doesn't care. So I've marked the first part already, this is all correct, so but I will go through um, every question now. Okay, so figure 1.1 shows this basic circuit. Then circle what is this switch. And this is a single pole, single throw, because it has one pole and it has one throw, so that's why it's SPST. So it's right here. Then the next part, the LED has a 4 voltage of 2.1 volts. Calculate the value of R1 if the current is to be limited at 15 milliamps. So basically we just need we need R is VI, and we need the voltage here, which would be we need the voltage across the resistor lah. And due to KVL, we know that R1 and the LED share 9 volts. Since we know that the LED will eat up 2.1 volts, then the voltage at R1 would be 9 minus 2.1, which he has here. Then we divide by the current which we want, which is 50 milliamps. He converts the prefix, which is correct, and then he gets 460 ohms, which is correct. So that's correct. Choose which resistor is best. In this case, 470, because um, it is closest to 460, and also when you're using resistors to protect components, in this case the resistor is to protect and limit the current for the resistor, for the LED, right? So we also want to choose a higher value. So in this case, right, if let's say 460 is our calculated, and then we have 455 versus 470, right? Choose 470, because even though 455 is closer, in this case, since the resistor is protecting the LED, then we need something that has higher resistance. Yeah, so that's that. So he's correct here as well. Then draw an LED showing two physical features that allow the identification of the cathode. Oh wait, no, this is wrong. Wait, this is wrong. Because what this question is asking for, I think, is this is to draw the actual LED and then draw this. And then uh, in this case, current actually flows this way, and then this is the cathode. Damn. So, yeah. Okay, that's a cathode. Next, list shows a number of capacitance values. Complete the table. Show the capacitance values ascending order, lowest to highest. Okay. Pico, nano, micro. Okay, this is correct. Then so this will be in picofarads. Yes, it will be 47. And then the tree. Oh, okay. So for the getting capacitor values, right? The value will be the first two numbers. Then the third number will always be the number of zeros at the back. And then in this case, it's always in pico. So he is correct. This is correct. Describe what is meant by working voltage of a capacitor. Voltage applied across a period that should not exceed the maximum value, or it will be damaged. Uh, I would have also added. That it is also the amount of voltage required to charge the capacitor. I think adding that won't hurt. So yeah, okay. Alright. Alright, next. Two, okay, AC and DC, and then, oh, okay. AC signal, DC signal, yep, alright. Oh, wow, okay. The signal in A is modified. Frequency is doubled. Peak to peak is 2 volts instead of 4. And the DC level is 1, okay. So the frequency is doubled. So here we got 1.5 waveforms, so we should get 3. 1, 2, so this is wrong. Because in the Oh, with a duration of 1 second. Oh, I see. What's this working, bro? Okay, wait. Let me work out if he's right. So the old frequency, the old frequency would be 1 divided by 0.8, which is something, which is 1.25 hertz. So then the new frequency will be 1.25 times 2, which would be 2.5 hertz. And then with this we can work out one period. So one period, oh sorry, t is represents period, will be 1 divided by 2.5, which is 0.4. So it takes 0.4 seconds to, oh yeah, he got it, because yeah, so this is correct. Because one waveform takes 0.4 seconds each, so he's correct for the period. Then for peak to peak, it is 2 volts. He's correct. DC level is 1, so 3 marks. Table shows numbers. Oh, okay. Decimal is 91 and convert to binary. Oh, okay. So I'm going to use the calculator to do this. I'm not going to explain how I do it. I think I have a video on explaining how I do it, but then you can watch that if you don't know what the hell is going on. Okay, so he is correct here. This is correct, but I would have preferred him to not do this. Don't need last zero. You don't need the last zero because we are just representing it as a number. Even okay, but although they did add the 3 zeros here, but I don't think it's necessary. It's not necessary, yeah. And in this case, wait, I didn't check if he's right. Hold on. 3 is, oh, I can do this in my head. 3 and 2, yeah, he's correct here. And in this case, you need because in BCD, right? Okay, I'll explain in further detail in the binary video, but in BCD, each digit, right, has to be represented by 4 bits. So that's why it needs to be in 4 bits. So this is correct. This is correct. Still one advantage and one disadvantage of using BCD rather than binary. Easier than binary to convert, that's true. BCD requires more work. Okay, I'll accept that. Okay. Give one example of a number in 4-bit binary that cannot be converted to BCD comprising of 4 digits. Yeah, this is correct. Because in BCD, this would be 0001 and then 0000, which is 8-bit binary. So he's correct. Okay, a situation I can describe, blah blah blah. A safe in a bank needs 2 keys to open it. The manager and the director of the bank have the, okay. Security has a different key. To open the safe, the security officer must use his key. Either the manager or director can use their keys. Okay. So manager, director, security, yep, this is correct. NOR, NAND, yep. Convert your solution to use the lowest number of NOR gates possible. Convert your solution in A to use the lowest number of NOR gates possible. Yeah, he's correct. Non-inverting amplifier. Calculate the gain. 6 amps! The gain is 6 amps, lovely. Okay, hold on. So this is a non-inverting amplifier, and this is the equation to get the gain of the non-inverting amplifier. If you don't know what anything of this is, you can watch my video on amplifiers. But there's no unit, I think. There's no unit for gain. So do I want to minus his mark? Yes. You get 2 marks instead of 3. Okay. Complete the inverting amplifier. Inverting. So yes, it's connected. Yep, yes, it's correct. Input. Oh no! Oh no! This is bad. Oh, this is bad. Okay. Okay, oh, this is my fault. Okay. Impedance, state the input impedance value of an ideal operational amplifier. Impedance means resistance, but AC. Because typically you want the gain of an op-amp to be infinite, not the impedance. So, yeah, okay, you want infinite resistance at the input, so that's wrong, obviously. So, yeah, no. 7.1 shows a temperature sensing circuit. Okay, BJT. When the temperature rises, okay, 3 marks then. Give two advantages of a transistor. Okay, automatic undergoes biasing. It is, it is, um, hold on. Oh yeah, okay, you may wonder if, in this circuit you need a flyback diode because, this is a buzzer, and buzzers have, what? Buzzers have coils of wire in them, which will release energy when current stops flowing in it. You can watch my video on something. So basically, you need a flyback diode lah to protect the BJT, but they didn't ask for it here, so it's fine. Um, oh wait, include any additional components required. So no, you need a flyback diode. Okay, credits to Drovaya for telling me that. All right. Um, it is automatic. I can accept that. It undergoes biasing. So no, I don't accept that. Whoa! He wrote out every single letter. Damn, bro, this guy. Okay, anyway, digital counting circuit using a mechanical switch often suffers from contact bounce. Yes, when a mechanical switch is opened or closed, its contacts will connect and disconnect several times before a firm connection is established. Okay, good enough. 1 mark only. So output voltage will bounce between, yes, at a steady level. I mean, okay, I'll accept this. 1 mark. The bounce switch constructed at SR latch. Okay, so this would be, eh? Um, okay, I'm not sure if this configuration is correct. I'm gonna Google it because I don't memorize it. Let me see. So this this would be, because you're powering this, right? Oh, and your reset is always 0. So if you were to set 1 here, it's always 0. Give me a second, sorry. Set reset. Reset is always 0, so okay, wait, I'm gonna draw the truth table. So I'm just gonna do A, B, Q, Q, Q1, Q2. Let me draw a truth table real quick. So I have a video on SR latches, so you can go and watch it out. Check that out if you're interested to know more. So when okay, B is always 0, so we can remove the cases where B is 1. When A is 1, Q1 will be 1, so, oh, this is correct. Yep, this is 4 marks, correct. Okay, counters comes 16 pins. Draw in the space 16 pins. Show how first is identified. Okay, this is nice. 1, 2, 3, 4, 5, 6, 7, 8. Yep, there's 2 marks. Figure 8.2 shows an incomplete timing diagram. Yep. Increases the count by 1 every falling edge. So this is correct. Output QA, QB, QC. Huh? Wait, this is wrong. This is wrong. Every falling edge, then this is a falling edge. Then why doesn't your A increase here? So this is wrong. Also, even if this was right, when this falls, this should increase, then this should remain high. So the correct configuration would be this. I'm going to draw it a bit higher. It will be this, and then because it's QA, it'll keep alternating. QB would be oh shit. It'll be 0, and then high, and then low, and then this would be this would be 0 all the way. Right, because 1, let me use my hands. 1, 0, 1, 0, 1. Wait, 1, 0. Oh, okay, wait, I'm wrong. But okay, but this dude is still wrong. So 1, 0, 1, then it will go up here. 1, 0, 1, 0, 1 is still up. Then when it reaches 0, it goes down. And then this will be high. 1, 0, 1, 0, 1, 0. So it's up here. And then throughout this is this. Yeah, so this is the correct one. So he's wrong. 0, I think. Oh, okay. When it's 0, I'm not going to indicate anything. Yeah, he's wrong. He's just wrong. Outputs from the decade counter displayed on 7-sec display. 8.3 shows a decoder. Yeah. 7 segment. Oh, and the pin diagram they give you. Okay, that's quite nice. So draw the connections between decoder and okay. Oh, I don't accept this. Okay, look here, guys. Do you see this? I can't tell what wire is. I can't tell what wire is what because it just all enters and it exits. So I can't say if this is correct. Wait a second. Why are these connected to this? What? What? You don't need what? You just need to connect this to this. What? These are your inputs. These are your inputs. B not connected either. Oh yeah. Oh! Okay. So because of that, I have to give him 0. Unfortunately, you don't get any marks. Cause also this, like, I mean, what do you want me to do? So I'm not even gonna go through this. You just need to. Oh, should I? Okay, I'll just go through a few wires because I don't want to waste my time. This is like 7. So like E, they say pin 1E. So E needs to connect to pin 1. Another example is like D to pin 2. Oh, okay, D needs to go to pin 2. Like that. That's it. That's it, okay? I'm not going through this because it's just connecting dots. Damn, bro. How do you... Okay. Shade the 7 segment display show number. Okay, yeah, this is 3. So, yep, this is correct. This it's a common cathode display. So at the COM pins it would be 5 volts. Are you sure about that? I just opened Instagram on my phone. Are you sure about that? Yeah, you're wrong. It's 0 volts. I knew something was weird. Okay, I have a video explaining this, so it's fine. Yeah, I have a video on 7 segment displays. Okay. Um. Okay. So yeah, moving on. Figure 9.1 shows a 555 monostable circuit used to school bell. Okay. Okay. State how the circuit is triggered. It is when the multi-vibrator is activated. So that's obviously wrong. It's triggered when the switch closes. That's all you had to say. It was 1 mark. It is when the multi-vibrator is activated. Yeah, okay. Describe how the duration of the bell operates can be calculated and changed. Can be calculated by yes. Can be changed by increasing. Yeah, okay. Yeah, this is correct. So this is correct. Um, uh, R2 is a 1 kilo. One benefit of using this resistor, it is connected in series. The benefit is that your I mean, my answer is gonna be not gonna be that good, but this is even worse than my answer. My answer is your default resistance will be 1 kilo ohm, so that your input will always have a resistance. Because if at that place it will be 0 ohms, right? Then your period output will be zero, or yeah, your output will be nothing. Because if let's say you didn't have a base resistor, and then let's say your resistance here is 0 ohms, then using the equation, then T is 0. Then your output will, when T is 0, basically your output will show nothing lah. So you need that default resistance. That's why that's the benefit of using R3, using R2. So this is wrong. It's been decided the bell should turn on and off. So A stable 5 timer of an A stable. Yep. And then missing components. Yeah, this is correct. Oh, oh, okay, yeah, this is correct. I was wondering why this is like a random thing here. Okay, yeah, this is correct. Oh, wait, let me change the tick to here. Bell needs to turn on and off with a frequency of 2 Hz. So calculate the component X. So 2 Hz. So T is 0.5, yes. T will be this equation, yes. 0.5 will be this. And he let some of the... Oh, okay, this is just plugging in the values. So, I mean, if you calculated this correctly, then you should be right lah. So I'm just gonna say yeah. I'm not gonna check. An output transducer requiring a higher current need to be operated by relay. State one fact that would need to be considered when choosing a suitable relay. The relay operates using magnetic fields. Okay, Vic. Okay, I'm not saying he's wrong. The one thing you need to consider is that a relay will operate using magnetic fields. But then you can't just say that, even though it's 1 mark, I know, but you can't just say that. Yeah, why? So what if there's magnetic fields? The so what is that because it operates with magnetic fields, it deals with inductors, okay? And then with that, you immediately need a flyback diode. So for this one, you need a flyback diode. You need to say that there's a flyback diode, okay? But a better answer will probably be that a relay needs... Actually, no, this is fine, yeah. This was okay. It's just that you had to say the flyback diode thing. You can't just tell me, you're like, if a man is dying, you can't just say he is dying. You have to... Oh, why? Why is he dying? Okay. Incomplete relay operating circuit is shown in this. Connections, circuit Darlington driver arrangement to operate the relay. Dang. No, this is wrong. This is wrong. I will give you the Darlington pair is correct. This is correct. But it is about a relay, so I'm not gonna give you plus. 1 mark just because you did this, so you get 1 mark. Your relay is connected wrong. It is connected to 6 volts, so your relay will be constantly on. And you want it to be controlled by a BJT, right? So what you need to do is you can either remove the wire here and connect it like this. Oh, wrong. You can either remove this wire, connect it like this, remove this wire, and remove this wire, or I'll use a different color. I'll use blue. Or you can remove this wire and then do this. Yeah, that's like your only two options. So yeah, you just connected the relay wrong. So yeah, you get 1 mark only. Alright, next. Circuit is being developed to supply AC, to supply a DC voltage from AC, so full bridge rectifier. Oh, okay, or rectifier in general. Diodes can be used to rectify AC to DC. Input signal fed into, okay, draw on the figure 10.1 to show the output of the half wave rectifier. Mark the peak value of the output and then that, okay. So let's see. How much marks? 2 for each. Okay, you're wrong on both, and you get 1 mark each. The reason why is you did not consider this. You indicate here that the peak voltage is 10 volts or aga, I don't know, I can't really tell, but you're wrong. Because in the half wave rectified signal, the current actually goes through one diode, so the peak voltage will be 10 minus 0.7 volts, so this is wrong. And you get 1 mark because you drew the AC signal correct lah. Oh, you know what? No. You get 0 marks for both. Because I'm stingy. What you needed to include is that the peak voltage. Okay, you know what? No. I'll give you 1 mark each. What I was thinking is because your signal needs to be lower because it is 10 minus 0.7, but your signal cannot touch here. Okay, you understand why when you watch my what if you are good if you watch my AC oh my gosh, AC rectifying to DC video. So for that I was considering to just give you 0, but technically they didn't ask you for it, so I'll just be nice. I'll give you 1 mark each. Never consider VK on the duration also. What the hell is VK? I'm just gonna ignore what Jovaya just said. What I said. Oh, okay, cool. Yeah, so you get I'm being nice. I will give you this much only. Also, like, I mean, oh, but you do include it here. And then you decided to not include it here? I don't... Okay. Figure 10.2 shows a full wave rectifier, yes. Describe how this circuit operates. Okay. Okay. Okay, so I'll explain it now. Basically, right, when you're rectifying AC, when you're rectifying AC to DC, right, you have to use a full bridge rectifier, or when you're using a full bridge rectifier, there's 3 stages in the rectifier. That's why you got 3 marks. The first stage is this diamond of diodes. Second stage is a capacitor, and then the last stage will be usually it will be a Zener diode, but there isn't one here. So 3 marks. 2 marks is probably for the diamond. I'm not gonna explain it here. Watch the full bridge rectifier video. I'm not gonna explain it here. Okay. DC supply from the rectified can be regulated using a Zener diode. Nice. Zener diode has a breakdown voltage of 5.1. State the output circuit at 10. No. Your output will be 5.1. Watch my basically, right. A Zener diode operates. The way a Zener diode operates is if the voltage across it, right, is higher than its breakdown voltage, the voltage across it will be its breakdown voltage. So it won't be 5.9 volts. So since it's 11 volts, right, it's higher than 5.1. Therefore, the voltage at the Zener diode will be clamped to 5.1. So this is wrong. Explain the meaning of 1.3 watts rating. It is the maximum power the Zener diode can contain. No, I don't accept this. You have to say is the maximum power that it can handle before breaking. So this is wrong. You have to include the before breaking thing. Calculate the maximum safe Zener current. Okay. Your voltage will be 5.1. What? Okay. 1.3 watts. PSVI. Yes. Okay. If the calculation is correct, you are correct. I'm not gonna check. So you get 3 marks. Draw the characteristics label with the breakdown voltage with the value of the breakdown voltage and the axis labeled clearly. Huh? They gave you the axis. Okay, never mind. So you didn't label the breakdown voltage. You didn't even get the value of the breakdown voltage, which is here. This is the breakdown voltage. So I'll give you 2 marks. I'll give you 2 marks. The water temperature in a tropical fish tank needs to be kept at 27 degrees Celsius. Water temperature is controlled. Switching on a heater cooler fan. Okay. When the sensing circuit detects that the water temperature is too cold or too hot, it will activate. Okay. Explain why this time period is needed. It will activate the timer circuit on the heater or cooling fan for 20 seconds before checking the temperature again. It is to activate the circuit so that the heater or cooling fan will react accordingly. Wrong. 0 marks. You need 20 seconds because if you immediately turn on the heater, then it will immediately become boiling. You turn on the cooling fan, it will immediately become 0 degrees Celsius. No. Decreasing, cooling or heating something, right, takes time. That's why there's a 20 seconds. That's the answer. Thermistor is in a waterproof casing used to monitor temperature. Statewide must be a waterproof casing. Thermistor is a good conductor of electricity. It can electrocute the... No, this is wrong. This is wrong because the thermistor operates at a low voltage of around like 5 volts, which can't kill. Also, it is to protect the thermistor. It's not to protect the organisms because the thermistor. I didn't know this, but I assume now that the thermistor is prone to damage from water. It's definitely not this. The waterproof case is to protect the thermistor. Yeah. Power of circuit diagram and temperature control circuit. Okay. Thermistor has a resistance of 59 kilo ohms at a temperature of 27 degrees Celsius. Using information, calculate the voltage at point X when the thermistor resistance is 59 at point X. So this is a voltage divider circuit that you just didn't do. So okay, since this is a calculation question, I will have to do it. So yeah, this is just a voltage divider. So the answer would be X would be 59 kilo ohms divided by 47 kilo ohms plus 59 kilo ohms times 9 volts. So let me get the answer for this. This will be... you know how usually I say you need to convert the prefixes, right? Since all the prefixes are the same here, I can just... And it's a division, so pretty much it's a ratio, right? So I can just calculate this separately, which would be 59,106 times 9 lah. Then after that we get the voltage there would be like around 5 lah. Around 5 volts. Okay. Oh, okay, 5.1 lah, but close enough. So yeah, signal from the thermistor is connected to two comparators. Take the 2 statements that are true for a voltage comparator. Okay, if plus is higher than minus, output is high, correct. Minus is greater, no. Plus, no. Yes, this is correct. 2 marks. Explain the changes that take place in the circuit so that the cooling fan switches on when the temperature rises above. When the temperature rises above, the thermistor will react first. Okay. With the temperature indicating a value more than okay. The current then flows to the top voltage comparator, okay, circuit, which will turn on the cooling fan. I mean, you're not wrong. That will work, yes. That's what will happen. But then, uh, okay, sure, yeah. I can't think of a better answer, so I'll give you the full mark. Yeah. Heater is rated at 12 volts, 550 watts. Calculate the resistance. Use that. They give you the formula, damn. Okay, if your calculation is correct, then this should be right. What's meant by power? The amount of voltage directly proportional to its current. No. No, uh that's not what it means. That's not sorry, that's not what's meant by power. Power is I'm trying to Google it here, but your answer is definitely wrong. Okay. Power is the rate at which electricity is consumed or transferred. That's what is meant by power. So you're wrong. Oh, and that's it. Okay. So let's tally up your marks. It's out of what? 100, right? So out of 100, let's see how much you get. I think you won't do that badly. You'll pass for sure. But let's see what happens. So 1 plus 2 plus 1 plus 2 is 6. Okay, I'm not doing that. I'm just gonna add your marks. I'm just gonna add your marks. Plus 3 plus 1 plus 1 plus 2 plus 3 plus 2 plus 2 plus 1 plus 3 plus 1 plus 3 plus 3 plus 2 plus 2 plus 2 plus 1. Okay, so section A you get 35 out of 40, I think. So you get 35 out of something. I don't know how much is out of, but that's pretty good. That's not that bad actually. Okay, let's see. 2 plus 4 plus 2 0 0 plus 1 plus 2 plus 3 plus 4 plus 1 plus 2. Okay. Yeah. Plus 3 plus 2 plus 2 plus 4 plus 2 again. What? Okay, yeah. So your section, oh damn. Your section B is 34. That's not good. That's just passing section B. So you're 34, so in total you got 35, right? Yeah. Oh, that's not that bad. You got 69. Hey, that's an A2, or that's close to an A2. You got 69. Yeah. Okay, so that's it. that's it with this video. Um, I hope you learned something from this. Yeah. From me going through specimen paper 1. Yeah. So yeah. Okay. Yeah.